Okay, so I have a good paper here. Hi, Celeste. Why Uranus and the other planets of the solar system are better prospects than Mars in understanding biological life. That is also the title and the abstract. It's the same thing. Written by Pardis Tabai Damavandi. I'm probably butchering that name. But basically, he reviews. I'm going to read this paper out to you all the way, but he reviews the idea that, we have a very strange atmosphere in Uranus to explore. There is a lot going on in there chemically, and he finds it strange how we don't consider the beginnings of life, or at least forming life, happening inside of that object when it has lots of specific gases such as H2S, which I think is sulfuric acid. I'm not sure. As well, the thick atmospheres can protect from X-rays. So if there's life forming right underneath the surface, there could be very complex chemical reactions going on in there and forming the precursors to life. Rather than looking at Mars and going, well, here's all the evidence where life was, and we're gonna try to figure out how life began by studying a dead star. But he hasn't linked stellar metamorphosis to his references page. Maybe one day he'll see the theory, but basically I can see where he's coming from. If you want the action, if you want the energy produced, if you want the chemicals to mix together in huge amounts, you go where there's lots of energy and lots of chemicals to be mixed in huge amounts. And that is in the Eurasian atmosphere. Same with Neptunian atmosphere, same as Jupiter and Saturn. Those objects are forming more and more complex chemicals as they cool, collapse, and evolve and become more Earth-like hundreds of millions of years down the road. For those that don't know, I have Uranus as being around 1.2 billion years old, Neptune about 1.1 billion. So they each have about 3 billion years to go before they reach Earth's stage of evolution. As well, Mars, I have it about 22 to 30 billion years old, so it's very much dead. But his argument here is you go where the action is. Suffice to say, that's a good viewpoint. I think that's a very well-refined viewpoint, especially since we haven't been to Uranus since it is only explored once by the Voyager 2 probe. How many years ago? Like 40 years ago. We haven't sent one up there since because it's just a ice giant. Nothing interesting happening there. But for those that understand the theory, we know better. But that being said, to understand life, you can go in both directions. Of course, Mars is a dead world, so there's, barely any life on it at all. If there's right underneath the surface, it's mostly dead. But it definitely did have life on it in the past. So you take the Earth, you have a dead star, you have one that's going to form life, and then you can extrapolate a very long sequence of events. You take Uranus, where it currently is, you have it evolve to an Earth-like state. And then you take Earth from its state right now, and you allow it to evolve considerably more, which would be more like Venus. Venus is older than Mars, but you can still look at Mars too as being a dead star as well, because that's what it is. And you can draw those connections. And that's why stellar metamorphosis exists as a theory, is you draw those connections between objects that appear disconnected. And as well, drawing those connections is the essence of stellar metamorphosis. It's hypothesizing in a way that pushes change and transformation and dynamic thought to the sciences versus static, forming as is, nothing's changing. Shut up and do the math equations. Don't ask questions. This theory changes all that. As well, we saw that type of mentality and a young man by the name of John Pennington. He died at 25 due to the yellow fever epidemic of 1793 when he was struggling to saving lives, and of course he got the yellow fever too and passed away. But before he died, when he was 21 years old, he had wrote some chemical and economical essays, and here's the cover of that book that he wrote. And here it says, "The connections between the theory and practice of chemistry and the application of that science to some of the arts and manufactures of the United States." And he wrote in quotes here to kind of sum things up. "It is a pity so few chemists are dyers, and so few dyers are chemists, and so few dyers chemists." And a dyer is somebody who, took chemicals and they dyed different cloths and different material, and the chemical reactions that took place were very advanced. But the dyers didn't really question why those processes were happening or how. And then you have the theory end where the chemists, they don't really know how to get stuff going. They don't know how to actually dye any material. They just have theory. They just have ideas that don't really pan out in reality. But to think if you had both sides of that equation, you actually had the people who were experimenting and you have the people who developed the theory, and you combine them together, then you could have more complex or more comprehensive understanding. And that's one of the main issues I'm running into. But I did my little twist on it. My little twist is the Earth has an iron nickel core that's been almost purified into iron nickel. Obviously there's osmium and other heavy elements, but very few of the other heavy elements rather than iron and nickel, to the tune of a few billion cubic kilometers of this material in the center of the Earth. How did that material get there? Now, you have geologists where they theorize that sort of situation. They say it's the iron catastrophe where all the iron just sunk there magically. Well, how did you get that iron and nickel to be pure? Okay, how did you get it to the center of the Earth in such gigantic quantities? It's an unimaginable amount of iron and nickel alloy. Yet, the geologists, they have never been to any smelting areas where they take huge electrodes and they melt down hundreds of tons of iron to pour it into huge ingots. Okay, no geologist does that type of work. They just work on theory and they look at the surface of the Earth and they write down notes in books and they teach in classes and stuff. But when it comes to the hands-on stuff, there's just no geologists in the smelting industry. Conversely, there are no geologists there are no geologists in the smelting industry, and there's no smelters in the geological sciences because they're busy making things out of metal in huge quantities. Okay, but if you took a smelter and you asked them, hey, how did the iron nickel core of the Earth form? They tell you something had to have melted all that down and collected it in the center, and that should have been there first. Okay, and also, how much time would it take for that to cool down in the huge amounts that it's cooled down in? Baz, I think you remember giving me an example. There was a large piece of iron where it would take quite a few days, if not weeks, to completely cool down to room temperature from being cast. Now think billions of cubic kilometers of material. How long would it take that to cool down? And mind you, just to melt it down to begin with and then cool it down. So there's even more time involved. So yeah, there's that. But basically just combining the two is the issue here, and that's what this theory is supposed to try to accomplish. And one final word, today is September, I think, 5th. It's 10 years and 2 days. And thank you, Baz, for putting that 10-year anniversary thing up on Facebook. It's been quite some time now, and I've learned a lot. And I've learned that science as we perceive it when we're younger is not the same science as an adult. It's not the same thing at all. There's pure science, and then there's science by funding and politics. And unfortunately, I don't know if there's going to be any combining of the two anytime soon. So I guess I'm just going to have to work on this theory continuously without any major recognition for it. But that's cool. All right. I guess that sums up this talk. Take it easy, y'all.